Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. Within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process. So within the second module, we are currently on the third topic, that is system calls, exceptions and interrupts. So if you have been following along, you know that in this topic, we are talking about system calls, exceptions, and interrupts. And in a way, each of these is a way for the user process and the operating system to communicate with each other, right? So in the previous video, we introduced the concept of exceptions. We talked in detail what is an exception, and we also saw a brief overview of the sequence of events that take place when we have an exception, like how it is dealt with and so on, right? In this video, I want to go over the flow of exceptions in a more detailed way, like what are the exact steps that happen from the time the exception an exception happens in the system to the point it is dealt with completely. It will be a more detailed view of the flow of exceptions, right? So without further ado, let's get started. So this is the diagram that we saw in the previous video. As you can see, this is the timeline of process execution, and here we have an exception. The exception that we have here is a privilege violation, right? The user process did something it was not supposed to do while it was in user mode, right? So here we had an exception, and as you can see, the control was immediately transferred to the operating system. The operating system handles the exception, and finally, after the exception has been handled, the control is given back to the user process. It could be the same user process or a different one. So this was a brief discussion of the sequence of events that happen when we have an exception. We talked about this in the previous video. So what we want to do in this video is that we want to take a more detailed view of the sequence of steps that happen here, right? Talk about each step in a more detailed manner and understand the overall flow of an exception. So let us start the discussion of the flow from the very beginning. So the first step that happens is the registration of trap at boot time, right? So what does it mean to register the trap? Basically, if you look at the flow of exceptions, here you can see when the user process misbehaves or does something which it is not supposed to do, then the CPU detects it and immediately transfers the control of the user process, right, to the operating system. So this immediate transfer to the operating system, when this happens, basically the execution is jumping from one location to another. To which location will the jump happen? So the jump happens to a piece of code which is known as trap handler. So whenever, even in the case of system calls, you have seen this, when the trap instruction is executed, the control is immediately transferred to the trap handler. And this piece of code, that is the trap handler, is used to make the switch from the user process to the kernel, because the registers and all, they have to be saved, and new now we have to change the execution to the kernel code, right? All of that steps that are involved in the switch from the user process to the kernel, they are taken place, basically they are performed in the trap handler, right? So that piece of code, that trap handler, that address is registered during the boot time. And when we say registered, we mean that that address is put to a well-known register. So once we have placed the address of the trap handler in a well-known register, whenever the CPU detects an exception or whenever the trap instruction of system call is executed, at that point, what will happen? Immediately, the control will transition from the user process to that fixed location, that is the address of the trap handler. And from there on, the handling of the trap will continue. So the first thing that we have to do is that we have to register the trap. Basically, we have to place the address of the trap handler in the memory, right? And this happens during the boot process. When the when the system is booting up, during that moment only, the operating system places the address of the trap handler in a well-known register, because once the execution starts happening from the user processes, this will be frequently required. When we make system calls or when the user process misbehaves, traps will be happening frequently, and we have to transfer the control from the user process to the trap handler, right? So this is the first piece of setup that is done by the operating system. So now let us look at the next step. So here we can see we have the CPU and the process, some user process is executing instructions. So now let's say the process does something which it is not supposed to. Here I have taken the example of division by 0. So as we know, if you are dividing two numbers, then the denominator should not be 0, because it is not supported and it is not possible to divide a number by 0. And when the CPU detects that it is being asked to divide by 0, it raises an exception, right? And when an exception is happened, what the CPU does, it immediately halts the process, the user process from which this exception has been caused. So here the misbehaving process was process A. It is immediately halted, and there is a transfer of control from the process A to the trap handler. So this jump that you see, immediately the program counter's value will be replaced by the address of the trap handler that we registered at the boot time, right? Apart from this, several other things also happen. First of all, when making this transition, we have to save the program counter of the user process, because we have to, when we are pausing the user process, it might be the case that we want to resume the execution at a later point in time when the exception has been handled, right? From the same point, right? The point, the instruction where we are pausing the execution, when we resume the execution, we have to start exactly from the same instruction. So first of all, we have to save the program counter of the user process. Then we have to raise the privilege level, basically elevate the privilege mode from user mode to kernel mode, because now we would be entering the kernel and executing kernel code. So we must be in kernel mode to execute, like continue further execution. And finally, as you can see, the step that we have already talked about, once the program counter has been saved and we have changed the mode from user mode to kernel mode, we jump to the trap handler, and the address of the trap handler has already been registered at the boot time. The same address is just used to replace the program counter. So as you can see, this second step is basically a trap. A trap is basically any kind of event like system call, exceptions, and later on we'll see even interrupts, which causes the transition from user process immediately to the operating system, and then the operating system has to take appropriate steps, right? So now the next step is that we have to handle the trap. So now, as you can see, we are executing the trap handler code, right? We jumped from the user process to this trap handler code. And what happens here is that the most important thing that happens here is that we have to save the remaining registers of the user process and then replace them by kernel registers. Basically, there are certain important registers like program counter, stack pointer, right? Page table pointer, and other general purpose registers which store the information about the execution of the current user process. So we have already stored the program counter. This is where the address of the instruction that is next, that will be executed next, is stored. So having stored that, there are several other crucial pieces of information that are stored in several registers that I just talked about. For example, the stack pointer, right? So the stack pointer points to the top of stack. And when we are executing a user process, when we are executing a program, we know that any kind of execution happens in some function body. And we have talked about this in great detail in the topic of address space, that the function is executed on a stack, right? We push stack frames from each for each function call onto the stack, and this stack pointer is very crucial because it tells exactly at which function we are currently executing. So the stack pointer is an essential piece of information, just like the program counter. Apart from that, we have the page table pointer. The page table pointer is like a pointer to the address space. We will discuss about this in great detail when we study the topic of memory management. You can think of the page table pointer as the pointer to the address space. Like in a computer system, there are several processes and each process has its own unique address space. So this page table pointer points to the address space of the current user process. So that is also required when the address space is very crucial and it is required for every memory access. So again, this is also a very important piece of information that is associated with the user process. Then there are general purpose registers in which the when the user process is executing, right, as we know, the operands are fetched into the general purpose registers, and whatever computation takes place, right, the CPU combines these operands and produces new values. Those temporary values are stored in the general purpose registers. So the contents of the general purpose registers are very important. They kind of store the overall state of execution as the instruction execution is happening. So if we want to halt the execution of user process, and if you want to at a later point of time resume the execution at the same state, like currently the user process is executing at some point. It has some program counter, some stack pointer. There is certain information stored in the general purpose registers. All of this is there, right? If we want to halt the execution of the user process and at a later point in time resume the execution exactly from the same state, first of all you have to store all of these registers safely in some place, so that when it is time to restore the user process and you want to resume it from the same point, then you'll have to use these registers values so that the execution can proceed exactly from the same point, right? So that part where we have saved the remaining registers happens in this trap handler, right? And also we populate the values of kernel, basically the registers which are associated with the kernel here. So once we have saved the registers which are the values of registers which are associated with the user process, now we can place the value of the kernel into the registers. For example, we save the program counter, we save the stack pointer. Now the kernel will have its own program counter. It will the routine that has to be executed, that will have its own program counter. The kernel has its own stack, as we'll discuss later, right? So the kernel has its own address space also. So the new register values, all of that, they will be placed in this trap handler. So first of all, we saved the important registers that were associated with the user process, and now we place the new values that are associated with the kernel, like the stack pointer, the program counter, the page table pointer, all of that values that are associated with the kernel, the new values are then placed into these registers. And when all of this happens, we can say the switch from the user process to the kernel is complete, right? Finally, when all of this is done, we jump to the exception handler. So this was the trap handler, which is very generic. It is only responsible for saving the user process information and switching to kernel. It is not doing anything special per se to handle the exception. Or even if, let's say, when we make a system call, when a user process makes a system call and then also trap happens, in that case, again, the trap handler is only responsible for making the transition. It will not do the exact operation that is requested. For example, it will not be responsible for executing the system call or the handling of exception. So that is a special routine. So now once the trap has been handled, the user process information has been saved, the new kernel information has been populated into the registers, basically saying the switch is complete, right? After that, we jump to the special routine that will now handle the exception. So after the trap handler comes the exception handler. So this fourth step involves the execution of a special routine that will be responsible for handling the exception. So we have talked about how the operating system can handle or deal with the exception in the previous video also. So there are several options. The first one, the most extreme step that the operating system can take, is that it can kill the offending process. So let's say process A had done something severe. For example, let's say it violated the privilege. It did something that is only allowed in kernel mode while it was executing in user mode. It tried to execute some privileged instruction or access some privileged memory location, or let's say there was a stack overflow or a segmentation fault. All of these are kind of severe errors, and the operating system deals with such offense by straight away killing the process. It terminates the user process, right? Other way to handle the exception in a more graceful way is that it can, let's take the example of the page fault or the breakpoint, right? So in case of a page fault, it is also an exception. But here, what is happening is that the user process was trying to access some data, but it was not present in the physical memory. It is present on the disk. So all the operating system has to do is to bring in that data from the disk to the physical memory. And in this case, the page fault is not a this is not a fault of the user process, right? It is not a fatal error or something malicious that the user process has done. It is how the virtual memory works. We'll talk about this in great detail in the memory management module, but here just the basic thing is that user process requested for some data, but it is not there in the physical memory, and the operating system has to bring in that data from the disk to the physical memory, right? So here the exception is not of a severe nature. Here we do not need to kill the process. We just need to bring in the data. So here the operating system can handle the exception in a more graceful way. It just has to bring in the data and handle the page fault, right? Other example is that of the breakpoint. Let's say the user process, the programmer inserts breakpoint at certain instructions, and when that instruction, when we hit the breakpoint, the CPU halts the execution of the user process. Again, this is not something like a fatal error. All the operating system has to do is to gracefully transfer the control to the debugger, right? So that the programmer can inspect the value of the variables, the state of the stack, and so on. So the point that I want to convey is that it is not necessary and not even required to terminate the user process always, right? Only if the nature of the exception is very severe, then the operating system goes on and terminates the process. At other cases, it will do something, it will take some preventive or corrective action to handle the exception in a more graceful way, right? And the final or another option is that it can allow, the operating system can allow the user process to handle the exception on its own, right? We understood this with some examples in the previous video also. Certain programming languages like Python provide this feature where the programmer can write the logic of handling the exception themselves. So this is the try block, the exception block that we saw in the previous video. So in that case, the programmer can themselves define what should be done when an exception occurs, right? So in that case, what the operating system will do, it will transfer the control back to the user process, right? And it will let the user process deal with the exception themselves. So this was about this fourth step, that is, once the control is there with the operating system, what should it do? It can either terminate the process, it can do some other action and handle the exception in a more graceful way, or it can also allow the user process to handle the exception on its own. So now that we have dealt with the exception, it is time to return back to the user process. So first of all, there are two cases. It could be the case that this process that has caused the exception, it is terminated and killed by the operating system. Then the process to which we will return, right? The process from which we will resume execution, it will be obviously a different process, right? So here the operating system also has to run the scheduler and select a different process to which it will return. Or if it is the case that the exception was handled in a graceful way, or the operating system allows the process to handle the exception on its own, then we will be returning back to the same process. So there are two cases: either we return back to the same process to let it handle the exception on its own, or we had terminated the process which had caused the exception and we will return to a different process. So all of that has to be decided by the operating system. Once the process is selected, once the process to which the return should happen has been selected, now we prepare for the return. So if you see, when the trap happened, we started execution at the trap handler and it saved the registers of the user process and switched to kernel registers, right? Now in the same way, while returning, as part of the trap handler only there is a piece of code which helps to return from the trap. So in that, we just reverse what we did in this step 3, right? So here now the things will happen in reverse, right? So first of all, we save the registers and then we jump to the exception handler. So this is the jump to the exception handler. Now first of all, we'll return from the exception handler, right? So this jump to exception handler, the reverse of this operation, you can see return from exception handler. So this is the jump and this is the return. And once we have returned to the trap handler, from the exception handler we have returned to the trap handler. So now we have a piece of code that helps in returning from the trap. So just like we saved the remaining registers, the registers of the user process, here we will restore the saved registers and switch to user process. So currently the values that we have in the program counter, the stack pointer, the general purpose registers, the page table pointer, all of that is from the all of that is related to the kernel. So now what we have to do, we have to replace those values, we have to change those values with the values of the user process, right? So we will use the values which were saved here. Let's say we are returning to the same user process, then we have to restore the values, that is stack pointer, general purpose registers, all of that, whichever registers we had saved, all of that we will restore. Let's say we are not returning to the same user process, then we will use the registers for that different process, right? Let's just, for the sake of convenience, assume that we are returning to some other process, that is process B, right? So process B also would have its own set of registers saved somewhere, right? So for that we will use, in this case, while returning, if we are not returning to process A, then here the register values that we will use will be that of process B. But the idea remains the same, either process A or process B. We have to change the kernel register values, right? We have to change the stack pointer to appropriate user process stack pointer. We have to change the page table pointer. Basically, we have to change the kernel related values, and now replace it with the user process values. Now those values could come from either process A or process B, whichever process has been selected to run next. Finally, after we have prepared for returning, right, now we are ready to return, but we have not yet returned, right? We have just placed the appropriate user process register values, right? We have not yet started execution of the user process. We have just changed the values to be the one that is required for the user process to resume execution from that point. So in order to return to the user process from the kernel, we have this return from trap instruction, right? So recall, how did we enter the kernel? This was automatic. Once the CPU detected an exception, it automatically made the transition. Here we do not require any instruction. In case of system calls, you do require a trap instruction to be executed because it is coming from the user process. The user process wants the operating system to come into the picture, right? Here in the case of exception, the user process is misbehaving. It is doing something malicious or buggy. Here the operating system comes into picture on its own. The user process does not initiate the process, right? So here in this case, we do not require a trap instruction. The trap happens automatically. The CPU initiates the trap. So the initiation of trap can be either from the user process, as in the case of system calls, or it could be the initiation of the trap could be from the CPU, as in the case of exception. But while returning, we have a common way. To return from this exception, we will use the return from trap instruction. And this instruction will again do the reverse of the things that we did while entering the kernel. So now that we are leaving the kernel, we'll just do the reverse of these things. So first thing that we did was we jumped to trap handler. So now we'll return from the trap handler, and we are now wanting to go back to the user process. Here we jump from the user process program counter to the trap handler. Now we are returning from the trap handler to the user process. And during the return, what else we will do? Here we raise the privilege level. So the reverse thing to do is the drop the privilege level. So while returning, the privilege mode will be dropped from kernel mode to user mode. While entering, we raise the privilege level from user mode to kernel mode. While returning to user process, we'll do the reverse. We will drop the privilege level from kernel mode to user mode, right? And finally, the last thing that we need to do is the change the program counter. We will use the same program counter that we had saved here, right? The first step that we did when the exception happened is that we save the program counter of the user. So we will restore that, and once we restore that, we can say the execution has been resumed from the user process, right? So this is how the return from trap instruction works. Obviously, the steps that I have indicated, they are only they're not exhaustive in nature. They're only indicative. There can be many more steps, but overall the idea remains similar. The implementation details can vary from one operating system to another, but the overall idea of handling a trap and the detailed steps remain the same, right? So let me quickly summarize the overall flow. Here you can see the first step is that the process, let's say process A was executing. Then it did something which it was not supposed to do. An error or an unexpected event occurred, which was detected by the CPU. The CPU detected the exception and immediately caused a transfer of control to the operating system. So it saved the program counter, raised the privilege level to kernel mode, and jumped to the trap handler. So the address of the trap handler we had already registered during the boot time. The same address of the trap handler we used to make this jump. Next, we are now executing in the trap handler, and we have to handle the trap. Here, basically, we will save the important registers that are associated with the user process, like stack pointer, general purpose registers, page table pointer, all of that which are related with the user process. We will save them to a proper place, and now we'll use some new values. These values will be associated with the kernel. Once this switch from user process to kernel is done, we jump to the exception handler. This was the trap handler. Its only purpose was to make the switch from user process to kernel. Now we'll execute some special routine. So here this we jump to the exception handler. Here now the kernel will do the operation that it is supposed to do, right? The very purpose for which this exception has been raised, here the kernel will handle that. It can terminate the process, or it can do some operation to handle the exception in a more graceful way, or it can it can start returning to the user process and allow the user process to handle the exception on its own, right? So now before returning, the kernel will decide which user process to return to. If the process A was terminated, then some other process has to be selected. Let's say the kernel selected process B. Or if the kernel wants or if the kernel allows the same user process to handle the exception on its own, then we will be returning back to process A only. Okay. So once the selection is made, we now are in the return path. So here we do the things in reverse. Whatever we did while entering, all of the steps we'll do in reverse. So here we jump to exception handler. Now we'll return from the exception handler. So the jump happened from the trap handler to the exception handler. So the return will happen from the exception handler to the trap handler. In the trap handler, we saved the registers of the user process and replaced them with kernel registers. Now we'll switch from kernel registers to the user process registers that we had saved. Once we have prepared for the return, now we are ready for return. Here we execute the return from trap instruction. Again, we do the exact opposite of the steps that we did while entering the kernel. Now we are leaving the kernel. So we'll basically here we are jumping to trap handler from the user process. Now we'll be returning from trap handler to the user process. We'll drop the privilege level and we'll restore the user process program counter, so that finally we resume execution from the process, right? It could be process A or process B. So this is how the detailed flow of exceptions look like. So a very important point is that let's say we are resuming from process A only, we will be resuming the execution exactly from the same point. The user process will not feel in any way that something happened in between. It will be basically exceptions or even system calls. The nature of these events are transparent. The user process resumes the execution exactly from the same point from where it had left off. So it is not kind of aware that something happened, right? At the exact point where we left off the execution, we resume from the same point. So all of this that happened in between, the user process is generally not aware of. So the point is that the nature of these events is transparent. That is, the user processes are not aware of that something happened in between. Many things happened, but in no way the flow of user process execution is disturbed, right? Obviously, if the process A is terminated, then that is a different case. But if it is, if you are resuming the execution again from process A, then we will be resuming exactly from the same point. So guys, this was it for this video. Here we discussed the overall flow of exceptions in a very detailed way, right? How we enter into the kernel, how it is handled, how we return from the kernel, right? So this was it for this video. We have now a detailed flow of the exceptions. We are done with exceptions, and in the next video we'll start talking about interrupts. So guys, this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.